I'm going to talk about the power of many. It's about a runtime system used to execute many large number of simulations concurrently on Blue Waters, but also other machines. I lead the Radical team back at Rutgers, sites there. Let me set the context and the motivation for our PRAC award. Whereas this is about a runtime system, the work is primarily, but not exclusively, motivated by biomolecular systems. Allow me to take maybe 5 minutes to set the context for the biomolecular systems and the kind of questions of interest. We all know that people like Klaus and others have been studying larger and larger biomolecular systems. The current status quo is about 10 million, I believe upwards to 100 million atoms. This represents the challenges needed to study, that need to be overcome to study such systems are the classical weak scaling, very large systems over a large number of core counts. And there's been progress there. The other type of problems in biomolecular simulations are those of long timescales. Some of you may know of the Anton's supercomputer, D. others, where 16 microns in a day. It's because many of the physical phenomena that need to be studied are truly long time scales. And just being able to study large systems is part of the problem, but not enough. You need to be able to study these large systems for very long durations. And the current state of the art is, let's say, milliseconds. Obviously need to push on further. However, if you look at the collective set of challenges in biomolecular simulations, it is not just weak scaling or strong scaling, but it's a complex mix. And let me give actually one example before I get into the details of this. And this is something that Bill talked, similar to something that Bill talked about, where in his ACI report, where if you're trying to study complex physical phenomena, just being able to study this in 1 dimension or 2 dimensions is often not enough. You simply get the physics wrong. And this is an example of how studying using a replica exchange system, trying to study protein interactions. When people studied this in 1 dimensions, in 2 dimensions, they just got it wrong. And it was only when they went to a 3rd dimension, in this case, a temperature, another exchange, and then a pH exchange, were they able to start to see the real underlying physics. So when you're studying complex phenomena of the type that you see in these biomolecular systems, it's not single partition strong scaling, not just weak scaling, but you have to be able to run many, many simulations to start getting these complex phenomena, if you will, exposed and to be able to understand them. In a nutshell, what I'd like to summarize this is you're not just looking at the long time scale, but as you get to bigger and bigger systems, you have this complex interplay. Bigger systems have longer time scales that you have to study. So the bigger the system, the longer the time scale typically you have to worry about. And if you think about where Moore's law is taking us, nodes are getting fatter, you see a fundamental problem. Let me reduce this, if you will, large complex set of problems into one specific problem, namely that of the simulation of the BPTI system. And again, this is done on the Anton's supercomputer. And you can see that for 800 milliseconds, or approximately 0.8 of a millisecond, beg your pardon, very little happened. It was in mostly a stable equilibrium state, no conformational, wild conformational changes. And the first wild conformational change happens around the millisecond barrier. As you know, very few people actually study systems, even small systems, but very few people actually study systems this far out. This really sets the stage for what is, by some accounts, both a philosophical but also a problem in the field, where are the simulations that are coming out of systems like Blue Waters and other high-performance machines, are they correct? Or as Wolfgang Pauli would say, they're not even wrong because they're not sampling enough, right? And this is a fundamental challenge. And if you will, this is the grand challenge: more sampling, better sampling, and faster sampling. I won't say too much more about more sampling in the specific context. Tom gave a very nice introduction today of how, in order to do adequate more sampling, you need to run hundreds, thousands of concurrent MD, and he gave several elegant examples. The PRAC project that we have is primarily aimed towards better sampling, and just to be clear, better and more are not orthogonal. You have to do a lot of these along with better. And what is better? It's to drive the system through intelligent analysis as the simulations are ongoing towards a point in phase space that has not been sampled before. So again, a schematic here to try to illustrate the issue. You start off with a point in phase space and you run many hundreds, thousands of simulations. At some possibly predetermined, possibly not predetermined point, you do a checkpoint, you do an analysis, collective variable analysis over all the simulations that you've done. And depending upon the results of that analysis phase, you may kill some, you may restart some, you may start some new simulations, i.e. you reweight a large number of simulations and you begin afresh in parameter in phase space. And you do this again and again. So this is the analysis phase is driving your simulations, many hundreds, thousands of them, towards the unsampled parts of phase space. And there are many different possible analysis approaches that you could employ. As part of this PRAC, we're doing the diffusion map-driven molecular dynamics and COCO stands for collective variables, a PCA-style approach. But the underlying ideas are very similar. You're trying to drive a large number of simulations towards an intelligent part, an unsampled part of phase space. Let me just take 30 seconds as an aside and point out that typically the interval between, let's say, starting and running these simulations and trying to do a checkpoint and analysis is quite long. It's maybe several minutes, possibly 10, 15 minutes. But in the extreme cases, especially when you're trying to integrate, let's say, some experimental data, I was talking to colleagues about integrating cryo-EM data, the time steps over which you'd run your simulation can be just barely few to tens of time steps, which basically means every millisecond to somewhere every second you're pausing to either integrate data or to do some analysis. We'll come back to this later. Okay. So as I said, I spent the first 5-7 minutes talking about biomolecular simulations, so that's what really has driven the PRAC project. However, as many of you will know, ensemble-based simulations are not only confined to biomolecular simulations or sciences, but they're pervasive. They're pervasive in climate sciences, and this is some example of running very large number of medium-range WRF hydro models. They're obviously pervasive in large number of geo examples, and something which many of you will hear about on Wednesday, and something that has driven a lot of activity in the past 1 year is the work of Paul Moran's team and the Polar Geospatial Center, where the Arctic DM reconstructions, that's also a nice example of ensemble-based approaches. However, it's important to appreciate that the ensemble-based approaches don't always mean a large number of non-interacting. Often, the ensemble members interact. And this is where life gets interesting, to say the least, because now you have to manage not only hundreds and thousands of concurrent simulations, but possibly hundreds and thousands of concurrently interacting simulations. And just to add a bit more of spice to that interesting state of affairs is the fact that often there are multiple different levels of interaction. So at the highest level, you have the interactions between groups of ensembles, and a slightly level below, you might have members within an ensemble. So you have a hierarchy of interactions between these ensembles. So with that, if you will, long motivation from a science point of view, let's now derive the set of requirements in order to have a runtime system that will meet the needs of ensemble-based simulations. So just to recap, you have heterogeneous workloads in many of these simulations. You have a combination of multi-node and sub-node simulations concurrently required to be executed. And then there's obviously the heterogeneity at the level that you may have MPI, non-MPI, and even different application kernels. The workloads are dynamic often. There's a whole set of reasons why the workload might be dynamic, and one could give a lecture on that itself. But just suffice to say that the set of tasks are not all known a priori. You need, as I alluded to, you need a range of coupling between the ensemble members and between ensembles. So these are, if you will, qualitative. Let's get some quantitative numbers. You need to support, for many of the science problems I alluded to, order 100,000 tasks. Now, some of these tasks could be single core, some of these could be single node, some of these could be many nodes. And the task size has this range. And if you just do your maths and you say, if you're talking about 100,000 tasks, you better have the ability to launch very fast. If you're going to launch one job a second, a lot of your time is going to be wasted. So you need to have the launch ability of at least 1,000, possibly more, tasks per second. And okay, just for variety, you then, just to add the fact that some of these tasks, there's a lot of heterogeneity and variation in some of these tasks. Some have to be killed because they've reached a part of phase space that is uninteresting. Some have to grow. So you can see, so you get the landscape of the requirements that a runtime system must be able to support. So just let's get this out of our systems. Why not the batch queue? Well, other than losing friends at the systems level, you probably just cannot get such throughput through a regular batch queue system. You have very little control over the concurrency. There's in fact limits. I don't remember exactly what the limit on Blue Waters is, but for most Exceed systems, it's somewhere between 10 to 100. I think if you're really yummy with folks, you can get up to 1,000. Maybe Paul did something special and got a few thousand. But that's it. That's the number of tasks you can run at a given time or submit to the queuing system. And there are a whole bunch of other reasons. The fact that queuing systems have different flavors, different, if you will, behavior. And if you kind of fine-tune towards one, then that's fairly fragile behavior if you move to another. So if not batch queue systems, then what? And this is where going back and thinking about how a large fraction of the distributed computing community has addressed a similar problem, but at a very different level, at a very different scale, and motivated by very different reasons, and that is called the pilot abstraction. A very simple schematic here is the fact that you're really going to decouple the workload from the actual acquisition of the resources. So let's see what happens. So think of these as your many ensemble members which you're going to execute, and these are the resources. Instead of submitting the jobs directly to the resource, you submit an intermediary capability called the pilot job, which acts as a placeholder. The placeholder job goes into queue. Once it's active in queue, the pilot job then dials up home and then basically gets access to the task. N number of variations in these details. Are they pull-based, push-based, so on and so forth? All those details for a moment can be ignored. The fundamental point is that you have the ability of a placeholder job, which then becomes a container for a large number of small jobs. And if you just pause to think about this, what this has really given you, it's given you very fine-grained spatiotemporal control over the resources that the pilots acquired. As I said, this concept is not new. There were pilot jobs even before they were called pilot jobs. I can see Dave smiling, and some of you might even know about this particular box called My Cluster back from 2007. I see Ed in the audience, and at least in this audience itself, there are three groups that have developed pilot jobs over the years. However, what is different is over the past few years, my team and I have been formalizing a theory of pilot jobs, formalizing the abstraction. Not all of these systems call themselves pilot jobs. As I said, there were pilot jobs before they were called pilot jobs, and we've been defining what are the necessary and complete properties in order to be called a pilot job. I won't get into the details, that's another talk itself, but for the first time ever, we have a common vocabulary across a slew of different pilot job technologies. And again, it's quite interesting to see how pilot jobs have evolved in increasing capabilities and assigned to onto a chronological scale. Okay, so the particular pilot job we're using to develop our runtime system is called the radical pilot jobs. No points for guessing why. Some distinguishing features, at least distinguishing features we'd like to claim, is that it has the first well-defined programmatic interface. Most pilot jobs have been used as an endpoint service. It's impossible, if not very hard, if not impossible, to build higher level services and capabilities on top of it. And you'll see the higher level services and capabilities we'll build. Radical Pilot is supporting production grade science, which I'll show you in a few minutes. But it's also a place where half a dozen PhD students are performing research towards high performance distributed computing. So this tension between production and research, I'd like to claim, is a tension we've overcome, and we have production and research capabilities in the same code base. And that's another story of how we managed to do that. And importantly, it's portable and interoperable over multiple different systems. It works on every Exceed system, works on most flavors of Craze, obviously works on Blue Waters. And that's really down to two features. One is it uses Saga as the access layer to batch queue systems, and obviously file transfers and others. Saga, for those of you who may not know, is a distributed computing standard developed over a course of 10 years, and Ed, amongst others, was responsible for initiating that effort. And the second part is the modular agent for different architectures. And this is the real hero of the show, of the efforts here, because this is, if you will, basic functionality. This is where the performance and scalability resides or dies. And again, this is just a very simple schematic. You saw a static schematic of the animation I showed you, just trying to tell you that eventually once it lands on Blue Waters, a lot of the performance is the Cray-specific agent, which I will now talk to you about. I'll just leave this. I won't say much here. This is for people who might want to get a better sense of the various subcomponents within the agent. But there's a very well-defined state model. And if you want to implement your own agent, you now have a well-defined state model as opposed to a black box, which many of the other pilot systems have. Remember, this is the tricky part of the pilot abstraction. So just before going further into telling you about the Cray-specific, let me just quickly tell you why we don't use pilot accessing the AP run layer, right? First of all, there's a lot of burden on the mom nodes being the Cray-specific nodes from which jobs are submitted. But there's also the limitations, the concurrency limitations I alluded to. None of these are overcome by AP run. So again, we're thinking of the design of the agent and at which of the many levels in the Cray system ought the agent be interfaced to. So this is, by the process of elimination, no AP run. Also something called Cray cluster management. Again, you don't do this, whole set of reasons. First of all, it's not universally available on all Crays, but again, there's a lot of load on the mom nodes, and amongst other things, there's a performance constraint that arises as a consequence of hitting the file system. ORTE, some of you may know, Open Runtime Environment. This is again being developed by the OpenMPI forum, and what we've eventually done is started interfacing the agent with the Open Runtime environment. Lots of details. Just want to tell you the reasons for doing this. First and foremost is that it now supports multiple tasks per node. Right? I told you that many of the systems pilot systems would not be able to submit tasks at a level of granularity less than a node. That's a fundamental problem. For example, Paul's work requires single core and as many single core jobs as possible. So this is one of the many reasons, but also it no longer hammers the file system because of the way that it interacts with what is something called the dynamical virtual machine. And all this, what this leads to is that you're no longer limited by simple fork exec behavior. You can do a lot of sharing of the sockets and files, file descriptors, beg your pardon, and you're no longer limited by the file system interactions. So as I said, there's a lot of architectural details. This is all published in a paper. We had a submission at the Cray user group meeting, and then others as well, where we talked about all of the architectures specific to Blue Waters. So I think it was one of the few, if not the only, Blue Water specific publications at the Cray user group in London a couple of months ago. And then here's the overall architecture. And again, basically a capturing of the main details. What's different between this slide and the previous slide is a very small subtlety. Here, it's using the command line, but what we've done working with folks at Blue Waters, but also with Ralph Cassin and others as part of OpenMPI, we've created an ORTE library where we interface with the ORTE library. And this basically has led to significant performance improvements, which I now talk about. So this is just to try to tell you that all the analysis I gave you is backed up by quantitative estimates. So this is the time to completion of a test workload. The test workload consists of 3 generations of tasks. Each task is 64 seconds long. And this is really trying, so if you think about it, if there were no overheads in the system, it would be 64 into 3, 192 seconds. And that's represented by this blue line. So you'd have 192 jobs finishing in you'd have, as you change the core counts, everything would finish in 192 seconds because that's what the workload requires. Okay, but you'll notice that as the number of nodes goes up, and thereby the number of tasks goes up, you can see that the time to completion for non-ORTE based methods starts shooting up. There's obviously a deviation from the ideal behavior of 192, but you do get the flat behavior, especially with the ORTE lib as opposed to the command line. So all the ideas that the system design are very basic, but a validation of that. If you go back and think about the design requirements to be able to eventually support 100,000, this is a long-winded way of saying we're not there yet. Our number of concurrent units that can be supported starts maxing out at about 16,000. There's lots of details here about the duration of the job. The single most sensitive aspect is how long the job's running for. So if you're running 18-hour jobs like Paul does, none of this is relevant because you will get your 16,000 tasks running on 16,000 cores without any problems. The problem is if your jobs are of the order of 10 seconds to 100 seconds, and then you have 16,000 of those jobs. And remember, I gave you a physical instance of why such short duration jobs need to be managed, and some of these jobs are full-blown several node MPI jobs. Okay, and this is just telling you that we're kind of leveling out at 16,000 approximately. We've gone up to 65,000, but it's not able to sustain. You do not see this plateau, even at durations of 1,000 seconds. And again, this is just saying the same thing in a different way, that the overall core utilization, that is the time that you've kept the core and how long you've been computing on the core, is sensitive to the duration of the tasks. Once again, if you're running jobs for hours, none of this matters. You're essentially at your 100% utilization. But this is just trying to say that the launch rate has been fairly carefully optimized to start being able to get short running jobs, about 64 seconds, 100 seconds, over a large number of nodes and a large number of, if you will, jobs. Work in progress. Just before you think that these are just toy workloads, remember the original motivation was to try to support these careful, if you will, simulation analysis workflows from the biomolecular space. In this particular case, there's GROMACS and a specific diffusion map approach, but there's also AMBER and COCO with the collective coordinates. Very similar behavior. We're not able to currently get uniform, perfect, strong, and weak scaling behavior. The answer is fairly simple. It's all about the file system interactions. That is the main killer right now, working with Blue Waters to try to optimize and fix that. So in my last minute or two, probably, just want to get to the kind of the design process. So I don't think I need to tell this audience why it is so difficult to build scalable, extensible, and flexible tools that work across large number of exceed Blue Waters systems. In a nutshell, in the interest of time, is generality is often orthogonal to performance. If you pin your platform, you can extract performance from that platform. But if you're designing to work on several platforms, then there is a give, and often that give is that performance. So how do you operate under this constraint? Well, obviously we're trying to find the sweet spot, but the approach is really the approach we've taken. We've taken general tools, at the pilot level, but the second general tool is take the agent and try to bring down the point at which the specific customization is required to the lowest level. So some of you who follow European politics, this is the level of subsidiarity. The changes have to be at the lowest level. And in this case, that is the ORTE interface to the pilot agent. Everything else above remains the same, right? And that's what we've done to get the performance, but not change the conceptual model of running pilots. And the same performance can be had on other systems. As I alluded to, although the focus has been on biomolecular simulations, there are many fields that will benefit from this runtime system, including bioclimate and polar. And what we've shown is 16K concurrent tasks, launch rate of 100, actually several hundred tasks per second. There's some details about what you need to do for your application right now. My last slide will be the fact that although we're at 16K, we have arguably a roadmap to get to the 100K, and in a way that does not impose any constraints on the workflow layers above. And just 2 or 3 quick points about what the current challenges are that we're overcoming. Obviously, it's an issue of agent communication. You have now, when you're running 100,000 separate units, separate simulations over 100,000 cores, the communication between the agents has limited throughput. So this is one area where we're working with, obviously, the deeper integration with the ORTE layer and several others. Just want to conclude by some of the references. If you want a quick overview of the pilot system, this is your friend. If you want a background on the theory of pilot jobs, this is the best reference. And if you want to get the reference that I was alluding to about on Blue Waters, how a lot of the optimization's taken place, this would be a good reference. With that, I'd like to end acknowledging the people who have made this possible, including Greg from the NCSA Blue Waters team. Thank you very much.